All right. So basically what we are doing is we are minimizing the difference between the red line and the black dots, which is the data. And so the variables we are tuning to achieve that minimization is what? Is this A, J, and the B's, right? And now if this is my objective function to be minimized, can somebody tell me what kind of function is this objective function as a function of these A's and B's? Quadratic, right? I mean, f is a linear function of these A's and B's. Remember, the x and y's, they are simply data, right? They are just the numbers sitting in your database. So the A's and B's are the variables you tune to achieve a minimum objective function. So after you plug it in, you get a quadratic function. So last lecture we started, actually the lecture before on Monday, we started different kinds of optimization. And we already know how to solve quadratic optimization problems, even if it's extremely high dimensional, right? How do we solve that? Well, steepest descent actually is a terrible way of solving quadratic optimization problem. It's a pretty good way if your objective function is very complex, and steepest descent is actually a pretty popular way of doing deep neural networks, when your function, like the relationship between the quality of the model also written that way, and your parameterization is very nonlinear. So people do stochastic gradient descent. And in this case, my objective function is quadratic.
Just take a derivative.
Take a derivative.
Yeah.
And set it to 0.
Yeah.
Right? Okay, so that's actually, so taking a derivative of a quadratic function and setting that to 0 is actually remarkably different from a steepest descent. So in what way is it different? Let's actually do a little bit of analysis. So let's say J is your objective function, okay? And if I take partial J, let's just take example, partial J, partial B. And here, let's actually exercise a little bit of what we studied last week, right? So J is actually an indirect function of these B's, right? So without substituting this fx into this equation and expand everything, is there a good way to compute its derivatives?
Tj df times df dv.
Yes, it's actually the summation. First of all, you have sum over all the n's, right? Partial j, partial f of xi, right? Then multiply it with partial fxi, partial b. So the good thing about partial f, partial b is it's 1, right? So this turns out to be this is equal to 1. So this turns out to be just a summation of I goes from 1 to n, partial j, partial fxi, which is what? Is 2 times fxi minus yi, right? So this way we can compute the derivative to b, and similarly the derivative to a is equal to the same partial j, partial fxi, but then it's multiplied by something that is not equal to 1. So let me say aj, and that is okay. So let me make it a little bit more clear. So this f is going to be evaluated at each sample xi. So this j is actually the jth component of the ith x, right? So let me make it a little bit clear. So this would be the summation of 2 times fxi minus yi times this derivative would be just a what?
Xij.
Yes. All right. So this way we can compute the derivatives pretty easily. Now by setting the derivatives to 0, we actually get a set of linear equations, right? We get a set of linear equations basically says that my summation of I goes from 1 to n of fxi minus yi has to be 0. And also summation of 1 to n fxi minus yi times xij has to be 0. So I get how many equations? And this is j goes from 1 all the way to the number of dimensions. I get n plus 1 equations, right? The number of a's plus 1, which is the number of b, right? And I solve it. So solving this, yes, question?
Why are we not considering that you also have different? Why are we saying AJ but on your?
That's because b is the constant term. So we are considering m-dimensional linear function. And the m-dimensional linear function, so let's say, first consider m-dimensional constant function. How many degrees of freedom does it have? 1, right? Because a constant function doesn't depend on how many dimensions you have. That's the dimension you have on B. Then you add the linear component. In an m-dimensional space, there is m linear relationship, 1 to each component, 1 to each dimension you can add. So then the linear form, we get m plus 1 degrees of freedom. If you want to add quadratic components, right, you have more, right? You have actually, it's a m by m matrix, but the upper diagonal, the upper triangular and lower triangular are symmetric. So that removes a little bit less than half of these components. You end up having half of m times m plus 1 or something like that. Many new components if you consider a quadratic regression as opposed to linear regression. And if you go higher dimensional, you just get more and more, right? I mean, that's actually the classical way before neural networks comes through. People how to do one way of doing nonlinear regression. And the problem is, as you can see, it scales very badly with dimensions. So just to go into 2 dimensions, you are introducing a lot of more parameters. Going to quadratic and the cubic and the 4th order in high dimensions, the number of parameters just explodes. But if you have low dimensions, it's actually not a bad way to do things. It's basically adding more terms into this function f, quadratic, cubic, etc. All right. So solving this problem, this linear equation of the gradient equal to 0, actually involves inverting the 2nd order derivative. Right? That's because the gradient is a linear function. I mean, if the objective function is a quadratic function of your design parameters, then the gradient after you take one derivative is a linear function of the design parameters. And then solving the linear equation involves inverting the matrix, which is the derivative of the linear function with respect to the design parameters. Right? If you have a linear equation, the matrix itself is actually the slope, right? The multidimensional slope. So the slope of the gradient is the Hessian, is the 2nd order derivative. Okay?